let's talk about the difference between the Houdini native volume and the VDB volumes. And in here, let's create a geometry node. First, we need to create an empty soft container. So let's dive inside. And in here, first, I'm going to create a polygonal piece of geometry that later we will going to be convert into volume. And for that, I'm going to this time add a torus in here. So let's add this primitive so that we have a nice circular hole at the center. So I'm going to first, let's lower down its radius, and we have this uniform scale. Let's increase the uniform scale and maybe further lower this down its inner and outer radius. And in here, I'm going to now convert this into volume. And first, I'm going to convert this into Houdini native volume. And for that, we have a node called ISO offset. Let's add this and connect this. And now we have successfully converted our polygonal geometry into volume. And same way, if we want to convert this into VDB volume, we have these nodes VDB. So let's type VDB from polygons. And we have that node. Let's add this, connect this in here and view this. And by default, VDB from polygon node convert our this piece of geometry into what we call the surface VDB. Surface VDB is still a volume. It's just displaying our this geometry as a surface, but it's a volume. It's not an actual polygonal piece of geometry. If I activate my selection tool, and here as you can see, I do not have access to its polygon, or if I change these 2 points, here as you can see, I do not have access to any of that because it's not a polygonal piece of geometry. It's a volume. Let me activate my this view tool. It's just displaying this as a surface. So surface is a kind of volume. We can convert this into fog volume. So in here, let's enable this fog VDB, and now we are creating 2 volumes. So one, we have the surface, and now we have this fog volume that is named to density. And we can check if we press and hold the middle mouse button, and here as you can see, we have a one VDB volume. And in here we have these 2 VDB volumes. The first one is the density, and both of them, we are calling both of them density, and that is not correct. We are actually calling one surface and the second one to density. Let me see why it's showing me that. Now we have this. We have these 2 VDB volumes. I think it was just a matter of refreshing our this nodes. Now, if I press and hold the middle mouse button, here you can see it has refreshed itself, and now we can see 2 VDB volumes because we are creating 2 volumes. And in here, we can see their name. The first one is the surface VDB because we are calling this surface, and the second one density. And we have their voxel size information. Here we have the voxel size on each axis, that is the x-axis, y-axis and z-axis. And we have the overall voxel size. So let me uncheck this distance VDB. So now we are only creating a one volume, fog volume. And now if I press and hold the middle mouse button onto VDB from polygons node, and here as you can see, we have one VDB volume, and we can see its name. And same way, I can name this Houdini volume as well. If I go into the ISO offset and middle mouse button, here you can see, we can see the one grid volume, which means that it is a Houdini volume. But in here it says no name because we are not assigning name to this volume. So to assign the name, let's go into the ISO offset, and here as you can see, we have the name field, and right now it is empty. So we can call this name anything. We can call this one, let's say my volume, by typing my vol. And now if I press and hold the middle mouse button, and here as you can see, we have the name appear. So we have one grid volume and we have the name. So maybe let's change this one to the same name as we have in the VDB density. So let's go into the ISO offset and rename this name and press and hold the middle mouse button, and here we have the name. What is the difference between these two volumes? So the difference is that Houdini native volumes, they are not sparse, and the VDB from polygons, these VDB volumes are more efficient because they are sparse. What does that mean, sparse? Sparse mean that if you take a look at this geometry, let me view my original geometry. Here as you can see, we have right here, we do not have any geometry information. We have the geometry right here. So we are adding voxels where we have the geometry, and we are discarding this empty space to save our calculation time. That is why these VDBs are more efficient. But these Houdini native volumes, they will just take a look at the bounding box of our whole geometry. So if I add a bound to visualize the bounding box, we have a node called bound that will draw the bounding box. If I press and hold the middle mouse button, here as you can see, we have this size. That is the overall size of our geometry. So these are the bounds, and we can create them by if we connect this here onto this bound node and activate. And here as you can see, we have this bounding box information, that is the overall geometry. I can view this and maybe template this, and here as you can see, inside of this bounding box we have our geometry. So the ISO offset, this Houdini native volume, will use this bounding box and add voxels everywhere inside of this bounding box. And here as you can see, we are adding voxel on all of this bounding box, and that is not an efficient way of calculating the volumes. So that is why we have these VDBs. They are more efficient, and we can actually visualize these active voxel. If we go into the VDB from polygons node and we can view these voxels where we have the voxels, we can create a VDB visualize tree node. So let's add a VDB visualize tree. Let's add this and connect this in here. And here as you can see, we are visualizing this, but right now the visualization is not accurate. So let me go into the VDB visualize tree, and here as you can see, we are currently visualizing these leaf nodes. So let me uncheck this, but I want to visualize the active voxels. So in here, let's enable the active voxel option, and here as you can see, we have these voxels represented as NA points. And we can change the visualization. Let's change this to wireframe boxes, or we can change this to solid boxes. And here as you can see, we have these 3D pixels, these voxels, only where we have the geometry. If I were to, let's say, increase the resolution, which means that we need to lower down the voxel size. And remember that we are manually saying that is the voxel size, and here as you can see, we have this box, these are the voxels, so we are adjusting its size onto the voxel size. Let's lower this down to a value of 0.05. I can continue lowering this value down to create more high-res representation of our volume. And here as you can see, we are adding voxels only where we have the geometry, and we are not adding voxels where we do not have the geometry information. So we are saving out a lot of calculation time. That is why we call this one VDB, that these volumes are sparse. And here you can see that we have this sparse representation of these voxels. But if we go into the ISO offset, these Houdini native volumes, let me increase the volume sampling to add more resolution. And I can same way, let's create the visualizer to view the individual voxels. And to actually visualize these voxels, we do not have a visualizer for this Houdini native volume, but we can create our own this VDB visualizer for our these Houdini native volumes with the warps. And for that, because it is an A volume, here as you can see we have an A1 grid volume. To work with the volume, we have an A volume warp. Same way we have the attribute warp. If I add an attribute warp, and here as you can see we have the run over method, the points, primitive and vertices, but we do not have option to run over volume, and that is because we have a separate volume warp node. So let's add a volume warp node, and here we have the volume warp. Let's add this and connect this in here, and what that will do, it will run over these voxels. Okay, because it is a volume and we are working with voxel, this volume warp will run over volume. So if we dive inside, we are in the same context. We are in the Vex builder. That is not another context. If we right click and take a look at the node, and here as you can see we have all of these same nodes, but it's just that we are running over these volumes, these voxels, and onto the attribute warp. Same way we are running over these points, but now we are running over volume. We are working with voxels. So let's dive inside the volume warp and let's dive inside. And here as you can see we have this Vex builder. This by default these node different, and we have additional bind node, this built-in bind node, and we are importing the density volume by default, and we are outputting as a density volume, so nothing is happening here. And that is why it is essential. It's actually not essential, it's just easier to just name your volume to density, because when you create a volume warp node, it is by default designed to work with the density volume. So here we are reading our density volume. So what I would like to do, I would like to add a point where we have the voxels, because we are running over voxel, every voxels. So I want to add a point. For that we have a node called add point. Let's add a add point node, and here as you can see, and for this one to add the point, it need the point position. So right now we are adding a point at the origin at the 0, and if I zoom in and maybe enable my point display, and here as you can see at the origin we have a 1 point, and if I were to adjust its position, I can see that this is moving. Let me uncheck this and visualize, and here as you can see we have the point at this position. Let me zero this out, but what I would like to do, I would like to control this point position where we have the voxels. So which means I can just connect this into the P. Now this P means the voxel position, because we are working with voxels, with volumes. So let's connect this P, and it will add point where we have the voxel. And here as you can see we have lots of these points. So these points represent voxels. Here as you can see, if I were to, let me template my bound, or maybe let's just view the bound and template these points, and here as you can see we are filling our entire bound with these voxels, and we do not have any sparsity in here. That is why these volumes are not efficient, and maybe we can actually add a box in here. And for that let me remove this, and to actually create this box type visualization, we can create a box in here. Simply just create a box node, and because we have these points, which means we can create a copy to points node. Let's add this, and that is the geometry that I want to copy, and let's use these points where we have these voxels. And before I activate my copy to points, let's go into the copy to points and enable pack and instance, so that we are packing our geometry. And now let's view this, and here as you can see now we have this scaling issue. First, it is right now it's working very slowly, so maybe let's lower down the uniform sampling to lower down the voxel size. and it's still lagging. Let me check. We have the back geometry. Let's view this. We are actually working with quite a lot of these voxels. So maybe let's lower this value down to even further. So now we have a much snappier interface because we are creating a lot less voxels. Now let's use the voxel size to set our this box size. If I press and hold the middle mouse button, here as you can see we have the voxel size, and its voxel size is 0.2. So what I can do, I can create an AP scale attribute in here to control my this box size, because right now if I were to just change the uniform scale and view, and here as you can see I'm just manually scaling down these boxes. But what I would like to do, I would like to create an AP scale value in here to procedurally set the scale of this box to accurately create our this VDB visualize tree, our this visualizer. And for that, let's import this voxel size attribute. Here as you can see we have this information present, voxel size. Let's read this and set this voxel size as an our P scale attribute. And for that, because we want to set our this P scale attribute onto our these points, which means I need to create a point triangle by creating point warp. We could use the attribute triangle to write our own VEX code, but I think it is much easier to just use the warp. So in here I'm going to create an attribute warp, and by default it is set to run over points. So let's dive inside. Inside of that, you know that now we are in the same VEX builder, but now we are running over onto these points. And to actually set the P scale, you know that we can create a point export node, and in here we just need to type the name of our attribute, and I want to create the P scale attribute. And to actually read our this voxel size attribute, these attributes are called the primitive intrinsic, because we have here as you can see we have one primitive. The volumes are in the primitive category. So here as you can see we have one primitive attribute name, and inside of that we have this density volume. So volume is actually goes into the primitive categories, but they are volume. So let's go into the attribute warp and onto the geometry spreadsheet, and we need to go into the primitive. So let's go in here, and here as you can see we have a name attribute, and its name is set to density, the same name that we have set it in this name field, density. So that is the same name. And to actually view this voxel size, this attribute, these are what called the primitive intrinsic attributes. And to view these intrinsic attribute, here as you can see we have this option intrinsic. Let's click, and here as you can see we have all of these intrinsic attributes, but I am interested in my voxel size, so let's enable this. And here as you can see we have the voxel size information, and it's 0.23 if I press and hold the middle mouse button. And here as you can see we have the voxel size on each axis, X, Y and Z, and its value is same in all of the axes. So that is called voxel size. Here as you can see voxel size, that is the value attribute. And to actually read this intrinsic attribute, let's dive inside the attribute warp. And for reading the intrinsic attribute, we cannot use the bind node. You know that we can read these attribute by using the bind node and typing the name. To actually read the intrinsic attribute, we have a separate node called primintrinsic. So let's add, and here as you can see we have this primitive intrinsic. Let's add this, and in here we need to define the file from where we want to read the attributes from, and we can either use this output of input 1, 2, 3, 4. So these are these inputs. Here as you can see we have these inputs, so which mean onto the file I can just connect this one, which mean that I want to read this from this very first input. And in here we need to type the signature and the attribute name that we want to read. And right now we are reading the transform and it is an a matrix. But I want to read my voxel size, and we know that voxel size is an a vector. Let me find vector 3. It has 3 components. Let's dive inside. Go back and check. Here as you can see, we have 3 values, which mean that it is an a vector. But we can actually change this. Let me go into the primitive intrinsic, and we can change this to float and type the name. What that will do, it will just only import this x value, this very first value. So we can actually say that it is an float even though it's not an float. And now we need to type the name of the attribute that we want to import, and I want to import my voxel size. That is the intrinsic attribute that I like to read. So let's click, and now it will import that and spit out from this in here. So which means, let me move this aside, and let's connect this in here. And now we are using this voxel size to set our scale, and I can check by going on to this, change this to wireframe shading to visualize this as wireframe. And here as you can see, none of the boxes are intersecting because we have set it the size accurately. So we have very accurate representation of our voxel where we have all of our voxels. All right. And here as you can see, we have all of these voxels fill inside of our whole geometry, and we do not have any sparsity. I can go into the ISO offset. I can play around with the max size to add more resolution. And here as you can see, as I continue to increase more resolution, my viewport is getting slower. And that is because we are adding a lot more voxels, and we are also adding voxels where we actually do not need to. And you know that we actually do not need to add voxel at the center, but we are still adding the voxels as well onto the whole bounding box. VDBs are more efficient, and you should always use the VDBs for creating your own volumes. And there is come time when we do need to convert, we do need to use our Houdini native volumes. And for example, the Houdini Pyro solver or Smoke solver, these solver use Houdini native volumes, and we simulate them into Houdini native volume, and later we will convert them to VDB to save out our disk space to actually take benefit from the VDBs. That is the difference between the Houdini native volume and the VDB volumes.